This is 2011, question 5. So in this problem we have our sphere coming down, and one of the key things is that it does say that it's moving at a constant speed, right? So basically it's in equilibrium. This is an identical problem to, what type of problem have we done before like this? The Millikan oil drop experiment. This is the Millikan oil drop experiment, except it's moving this time instead of being stationary. But since it's moving at a constant velocity, the acceleration is 0, and you'd solve it the exact same way that you would a Millikan problem. Okay, so anyways, let's look what we're looking for. We are looking for the charge. We're looking for the charge Q. Okay. Now I do want to point this out. On these variable only problems, you should definitely, as you're doing these, kind of circle this. You need to make sure your answer is only in M, L, V. Fundamental constants just means like little g or k or mu naught, something like that. But only these. So if you're not in only these, you need to keep going with your algebra. Okay, so the key thing with this is that we're imbalanced, right? Which means Fe is equal to Fg. So as it's falling, the force of gravity needs to balance out with the electric force, right? Let's just keep going. Fe, your equation is Eq. Fg, your equation is Mg. Okay, now can we just stop right here? No, because look, M is good, G is good, but E is not good. So you have to go one more step. So be careful. A lot of people will just stop right here. So we are going to go one more step. Remember V is equal to ED, or E is equal to V over D. So we're going to go V over D, Q equals Mg. Okay, let's rearrange it because they're actually asking for Q. Never leave it like this. So this would be D Mg over V. Okay, so let's just see. All right, M, we're good. L, well, L is just D, right? So let's just fix that. So we're going to write L, M, G, and then V is good too. There you go. You're done. Okay, that's your solution. Yeah. Oh, the negative. So don't worry about the negative. Okay. At this point, that's just telling you direction. So just kind of solve it here, and I don't know if they said magnitude. Yeah, they said magnitude. So whenever you see that word magnitude, you don't have to worry about the direction. Okay, that's it. So this was worth 4 points. Let's see how they scored it. Basically, for setting this equilibrium, you got 1 point. For doing the correct substitution, you got 1 point. And then the second substitution, you got 1 point. And then 1 point for the answer. So that was worth 4.
If you do put a negative, will they dock you down?
I don't know. I don't think so. Let me see if they say anything here. It doesn't say whether they would or not. I'm assuming they probably wouldn't. But just be careful of that. Okay, question 2, B. Okay, so here's the experimental data, right? We did some data here. We have our little plots here. And the main question is, why is there a gap? There's a gap between here, there's a gap between here, there's a gap between here. This is a tricky question. It's only worth 1 point. I remember when the actual students took this test, they all freaked out about this question, but it was only worth 1 point. So don't let one question freak you out for the rest of your test. Just move on if you don't understand what they're talking about. Does anyone know why there's a gap? So remember, think back to Millikan, and maybe that will help guide you on this. And actually, if you even looked at the numbers here, check out this number. This looks like it's about 1.6. This number looks like it's about 3.2. This number looks like it's about 4.8. What do we know about electrons? What's the charge on 1 electron? 1.6. What's the charge on 2 electrons? 3.2. What's the charge on 1.5 electrons? doesn't exist because there's no such thing as a half of an electron, right? So you can only have what we call quantized amount, or whole electrons. You can't have partial electrons, right? And so here the charge cannot be in between 1.6 and 3.2. It has to be a whole number of electrons, right? So this would be 1 electron, 2 electrons, 3, 4, 5, 6. And this is what Millikan did. Millikan found the actual charges here. Okay? Anyway, that was worth 1 point. Again, don't let those 1 questions flip you out. Okay, so anyways, the next question is, where is it? It's on the back. Okay, if the value of L is this, calculate the mass of the sphere. So you're just going to be using your equation, right, that you derived earlier. Where'd my equation go? My equation's right here, but you have to use the data from this. So you have to choose a point somewhere to use the data. So, you could use this one, you could use this one, or whatever. Doesn't matter, and you just would go over. Now this one, you probably all got slightly different answers, unless you recognize, that this has to be 1.6. So anyway, I would probably use a 1.6Q and 3000 V. You didn't have to use these. You could have used anything else. You could have used this one. You could have used the 1000. You could have used the 500. Doesn't matter. Okay, and then it's just a matter of substituting in to solve for m. Okay, so you would go, all right, 1.6 times 10 to the negative 19. Okay, equals D or L. What was L that they gave you? 0.05. Okay, we're solving for m. Little g is little g. And the V that I chose for my data points was 3000. Okay, so that's pretty much what you're going to be doing here. And then you're just solving for your m here. M was, see what the answer is, 9.8 times 10 to the negative 16. Now again, this would be slightly off, right? Depends on what numbers you use here, and that'll give you a slightly different number for this one. They would probably look at this, and as long as it's reasonable, like if you put 1.8 or 1.7 or 1.5. Negative? Oh, because of the negative thing before. Oh, negative 15? 9.8 times 10 to the negative 15? No, that would be good. That's perfect, yeah. Okay, this was worth 3 points. Basically, 1 point for selecting your data points that are reasonable, 1 point for the substitution, and 1 point for your answer. Okay, letter D. All right, so letter D, the problem kind of flips, right? So now it's a completely different question here. On letter D, we have our thing moving into the field, right? And so it's going to describe the motion of the sphere. Now you don't know what the charge of this is, but you do know when it enters a field what should happen to it. It should take a circle. So it's either going to go like this or go like this, right? So you basically should say it takes a circular path. And it's probably only 1 point, I'm guessing. 1 point, yeah. So for any indication that the sphere moves in a circular arc or a curved path, you got 1 point. Okay, then question 2 says, how do you know what the sign is? Or how could you use this information to find the sign of the charge? Well, you basically do what we just said. You would say, okay, if it's a positive charge, right, then you'd use your right-hand rule. So if we do a positive charge, let's just do it for practice. Which one of these is right? The one on the left or the one on the right if it's a positive charge? Okay, so we would go thumb follows it if it's a positive. X means into. My palm goes this way, right? So that would mean the force would be in this direction. Okay? So it would be going in that direction. So some kind of statement along those lines He'd say, assume, let's see what they said. Stating that if Q is positive, then when the sphere enters the magnetic field, it will move towards the right. However, if Q is negative, it will move towards the left. Okay, so something like that. 2 points is how you would get it. Let's see what the little note is. 1 point only if the description would move either left or right, but not actually doing it. So in other words, saying, well, you could figure out what direction it is without actually figuring it out. So you should figure out what the direction is. Okay? All right, number E, derive an expression. So this is one of these. I think I put this on your core problems. I put this on your core problems to know. So make sure you know how to do these types of problems. So we want to describe an expression for B so that the sphere barely makes it around the bottom. And again, we have our variables that we want to use. So just make sure your answer is in terms of those variables. Okay. Got some space. Here we go. Okay, so remember, FB is now going to be what kind of force? Just did it on the quiz, right? This is a centripetal force. So FB should be equal to FC. So BVQ should equal, okay, mv squared over r, right? All right, what are we solving for? We're solving for B. So let's see if we have enough of our variables here. So B should equal mv over qr. So once you've done kind of the initial derivation, what you're going to want to do is say, all right, express your answers in terms of m, good, v, good, q, good. Okay, L and R. Now R is the radius of our circle, right? So look at our picture. We're barely making it. This would be R. According to our circle, this should be like barely making it down here at the bottom. That would be our R. So how's R related to L? L over 2, right? So that should be your solution. mv q L over 2. Let's solve it properly. 2 mv over ql. This was worth 4 points. See how they scored it? Basically 1 point for this. Okay, 1 point for this, 1 point for this, and 1 point for the solution. So that was worth 4. Okay, any questions? Yes?
What wording would you look for to know if it's valency?
If it's what?
Oh wait. Oh, never mind.